I'm a consultant. I work independently. I also work through Solid Quality, who has a fairly big presence in Europe, but I have no idea whether they have anyone in Sweden. I think there's many of them in Spain and some of the other countries. I didn't really prepare much of a bio, but I heard someone say, well, why is my title so long? I gather most of you are familiar with the query optimizer. So the cost formulas are basically one element of it. Given that the optimizer is already kind of a specialized topic, why are we looking at such a very narrow range within the optimizer? Let's see. Okay, so this basically gives you the scope within the optimizer. The optimizer's got to be able to parse the SQL to make it into something the software can understand. Then you have to generate the possible execution plans. For each execution plan, it's made up of component operations. The cost formulas are the formulas that it uses to assess how much those operations cost. Then you have data distribution statistics that tells you how many rows and pages are involved. So you take the cost model and your data distribution, and you can calculate a cost for each execution plan. For the query optimizer in general, David DeWitt gave a keynote presentation at PASS in this last November, and I have a link to his slide deck, so it's a pretty good slide on the larger topic of the query optimizer. Okay, so I didn't really make a slide for this, but because about why are we taking a look at such a narrow scope? I think most people here are DBAs. How many are developer DBAs? And how many are admin DBAs? So it's like half and half, okay. So that means you're kind of like the database expert within your company. Have you ever had a poor performing query where you know there's an index, but it's not being used? Can you give a precise answer to the non-DBAs why that index wasn't being used? Okay, and so you're the database expert within your company, and someone has asked you the question and you can't give a precise answer. So that's why we're taking a look at this really narrow subject. Now, some years ago, I gave a really detailed talk looking at all the formulas, and it didn't seem to me that many people were that interested. So I tried to look at, okay, how do I make it into something that you can use? So I think I'm going to try to simplify this, and let's see how it goes. What are the possible operations within an execution plan? This is like just a short list. Index, seek, key lookups, that's some of the basics of database operations. If you can't use the index, you're going to do a table scan, and that might include a clustered index scan or an index scan. In databases, I hope we do joins, loop join, hash join, merge joins. There are certain applications that don't do joins, or at least not in the database. They bring back a set of rows, and they go bring back one row at a time from the other table, and they do the join on the application server. The way that works is it's going to kill your database. You're not going to get any scalability. The bigger machine you buy, the worse the performance is going to be. And usually those software packages, they charge huge amounts of money, which tends to make your boss's boss want to buy this really expensive machine because it was really expensive software. And what did I just say about the performance of this architecture as you go up on machines? Okay, that's not. Updates, which includes inserts and deletes, is also part of execution plans, but that's a very complicated subject, and Connor Cunningham has, I guess he has a chapter in one of the Inside SQL Server books on this subject. He's the Microsoft person who actually works on that part of the code. He's the head of it. So pretty much he covers it, and I'm going to stay away from it. and it doesn't really impact tuning too much. Mostly what impacts tuning are the select side queries. Parallel execution plans are also pretty complicated. I'm going to touch on it a little bit, okay? Actually, I do have an hour and a half, so I know that in an hour I can't get to it, or just barely. So I haven't given this talk in the hour and a half format yet. Okay, some references. For Connor Cunningham, you just do a search on Connor versus SQL. I believe that's his blog site. The past keynote thing on the query optimizer, I think you should just do a search on this part here. It might take you to this URL, one of these two, but for some reason you can't just enter it and download the slide deck. You have to go to one, click some buttons before you can get the slide deck. I don't know why they didn't want to make it complicated. I guess if you're not smart enough to figure it out, you probably shouldn't be looking at the deck. And it did take me several tries before I could get it downloaded. I post my material here, but I understand I put my slides on this, so I guess it'll be on the users group website too. And I put it out as PowerPoint. I don't convert it to PDF, so you can't steal the material. I used to work at Intel, and like how good you were is how often your slide deck was stolen by other people. So yeah, steal slide decks. Just say where you got it from, though. There's another person that writes on the optimizer, and that's Paul White. He's out of New Zealand. So here are some links to what he's posted. And he actually found some interesting DBCC commands that I'll get into later. Okay, I'm sorry, I did say. So yeah, why are we looking at this very narrow subject on the query optimizer? Well, it's about when is an index used and when is a table scan. Exactly. I've heard people make guesses. They're wrong. Some of them are on the Oracle side. I don't know exactly how the Oracle makes its decision, but I'm pretty sure it's somewhat similar to how SQL Server makes it, which makes their guess wrong. I'm not sure who on the SQL Server side took a stab at it. Questions? No? Okay. Okay, now you might get into a situation where you have this poorly performing query, and you find it. You look at the execution plan, you see it doing a table scan instead of using the index. Why isn't it using the index? We'll get to that. But let me force the index, and all of a sudden it runs better. Why did the optimizer pick the scan when the index is better? So the cost model is the model that the optimizer assumes is true, which is not necessarily what really is true. And this is why what the plan picks and what's really true for your particular situation can be different, and it can be different in a large way. If it was different in a small way, you're not too concerned. Given the way systems are today, you're not really concerned about 10, 20%. You're looking for the ones where you're off by a factor of 10, 100, or 1,000. It would be pretty bad if you're off by a factor of 1,000, but it happens. Parallel execution is really important because the processor cores that we're getting are not getting very much faster than they are. They have gotten somewhat faster over the last 3 years, but we're not going to get very much more out of the individual processor cores. So everything depends on our ability to use all the cores in our system. And if you have a big box, you could have 64 processor cores now. There's a couple, this slide should probably be moved later, but there's a couple of, oh, I'm sorry, I'm not talking about the settings, but if you look up these settings, there's some references that explain, in books online, there's some explanations about what the optimizer is. And basically it says the cost refers to an estimated elapsed time, not CPU, but time, in seconds, required to complete a query on a specific hardware configuration. The other one gives a slightly different thing. It mentions the serial plan. It doesn't mention what the specific hardware configuration is. But you have to consider that these formulas were more or less set in place prior to with SQL Server 7. That means they were set before SQL Server 7 launched. There were some changes from 2000 to 2005, but fundamentally they're more or less, the basic structure is there, which means the reference hardware is on some machine that existed in 1996 or 1997. And from there we can make some assessments on, make some sense of the formulas, but we need to get to it first. There's nothing wrong. Okay, sure, the world has changed since 1997, but the Microsoft position is that people have gotten used to the cost model as it is. If they change it, they may improve it for 95% of people, but in 5% of situations, it'll be worse. And it's always, those people will call and complain very loudly, so that's why they're afraid to change it. I talked to some of the Microsoft people at PASS. They say there's talk about changing it, but they're all afraid of all the one or two cases if something bad happens. They know they're going to get horrible complaints. Now, let's see, earlier I mentioned Connor Cunningham from Microsoft wrote about the updates and deletes. He actually wrote a lot of the code for it, so pretty much he can tell you, because he knows what the code is. Microsoft doesn't want to share SQL Server source code with me, so the only way I can do it is kind of reverse engineer it. So let's pick a table. If we go to AdventureWorks, which used to be distributed on the CD, but now you have to go to Codeplex too. There's a table, sales currency. You type in SP space used, or actually you look in the partitions table, DMV. You see that there are 105 rows, 8 kilobytes data, 24 kilobytes on the index. I take it there's more than one index, but the fact that data is 8 kilobytes means all the data is in one page. Why is that significant? Let me take a look at these three queries. The first one is just select star from the table. Give me all rows. How many logical IOs is that going to generate? One, because there's one page in the data part, right? I can also do select star from where currency code equals. And oh, by the way, this is the cluster key. Now this used to generate 2 logical I/O because it would go hit the cluster key root level and then the data page, the leaf level. I'm not sure if that's changed. And finally, I'm going to use the index on name, which is a non-clustered index. So now let's take a look at the execution plan for these. So the first one is a table scan, but it involves one page. In essence, this is the second one is a clustered index seek. And you notice both of these have pretty much the same cost. They only differ by a little bit. And it kind of makes sense. Scanning one page and doing an index seek is about the same thing. If I use the non-clustered index, notice that the overall query is about twice as expensive as this one. So 50% of this query is about equal to that operation there. This is a clustered index seek. This is a non-clustered index seek. So basically those two are about the same. And the other half of this is the key lookup because I use a non-clustered index. I found my row. Now I have to get the rest of the columns in that table. I believe, yeah, because I did type select star. And This is just demo, so I'm not saying write select star in your queries. So just a few months ago, I had a DBA put out an edict, take out all, I don't want to see any select stars in the code. And so basically someone went with all those if exists, if not exists, and changed the select star to select count. You don't need to do that. Yes, there's issues with select star, but if it's a if exists, select star, if not exists, that's fine, okay? Okay, anyways, we're diverted. But anyways, the key lookup is also about the same cost as an index seek. And also, I'm sorry, this query just affects one row. Now let's go take a look at the detail for this. This one is a clustered index scan. The major point I want you to look at is the I/O cost, 0.003125. Okay, now let's take a, notice that this has an I/O cost, a CPU cost, a number of execution, the estimated rows. Okay, I might get to it later. I don't know. Okay, this is the clustered index seek. The I/O cost is the same, 0.003125. The CPU cost is a little bit lower, same number of executions. So the I/O costs between these two are the same. The CPU cost is a little bit lower. It only affects one row, whereas the table scan affected all 105 rows. Here is the non-clustered index seek with a key lookup. The non-clustered index seek, yeah, it's a little small, but I wasn't sure. I guess this made it pretty big, so I didn't need to make this as big as I did, but I didn't know that. So, but anyways, the non-clustered index seek is just the same as a clustered index seek. The I/O cost is the same, and even the key lookup has the same I/O cost. So in essence, it's saying if I scan one page, it's the same if I do a index seek for one page. Index seek for one row. Basically, I navigate the index. And then if I do a key lookup, they all have the same I/O cost. Let's see. And if I pick the table that didn't have a clustered index, the I/O cost is the same. So it's nice to know there's some constants in SQL. So if you were to put a formula behind it, if I'm going after more than one row or one page in a table scan, what is the formula? It's 0.003125 plus this number. The bar just means that sequence repeats. So, you know, how do I know it repeats exactly? Because it only gives you so many digits. Well, you try out expanding tables and you know that it's exactly that. The CPU cost is basically this number here plus this cost per row. On the I/O is per page. The incremental is per page. On the CPU, the incremental is per row. If I did key lookups for multiple rows, I don't quite pay this I/O cost per row. It's a fraction of the number of rows because if I do the assumption that makes the optimizer is that when you start, all pages are on disk. So the I/O cost, you're doing a disk I/O to load it into memory. But on the subsequent I/Os, on the subsequent key lookups, it considers the fact that this page may have been loaded into memory. And there is a formula for that. It's that thing with the parentheses and the two numbers. It's been a long time since high school math. I don't remember. I don't have any children, so I can't borrow their algebra book. Mine was kind of burned, lost, whatever. But as you know, I was looking at the formula, trying to figure out what the formula is, and after a while I said, wait a minute, I've seen this before. Okay, yeah, that's what it was. Okay, so this number is kind of hard to work with. So you're like, what is it? Remember it said the cost, I'm sorry, the planned cost was the estimated time in seconds. Well, if I invert that, that's per seconds. So if I invert this number, I get, I'm sorry, this number is 1 over 320. So in essence, it's the key lookup cost structure says I can do 320 IOPS. Now, if I'm doing a table scan, I do pay this cost once, but on the subsequent pages, I'm paying this cost. If I invert this, I'm sorry, this is 1 over 1350 exactly. That's if you have the bar up here. So in essence, the optimizer says when I do a table scan, I'm scanning 1,350 pages per second. If I do a key lookup or even a loop join where the I/O is essentially assumed to be random, it's 320 per second. Now a scan, if you want to work it out, it's 8 kilobytes per page. That works out to 10.8 megabytes per second. So the way the optimizer works is, if it's sequential, we do 10.8 megabytes per second. If it's random, it does 320 IOPS. Now, earlier I mentioned this formula was more or less set in SQL Server 7 days. That was, okay, SQL Server 7, I believe, launched in 1998. I don't have the exact, I'm kind of hazy on what happened back then. So that means the formula was probably set in 1997. What hard drives were available back then? I do not believe 15K drives were out then. I think you had 10K drives, but those were brand new. So it could have been based on 7,200 RPM drives. 320 IOPS would correspond to 4 7,200 RPM drives. The best I could figure out, disk drives back then had a sequential rate of about 4 or 5 megabytes per second. So you can kind of guess that this reference system may have had 2 or 4 hard drives in it. So it may have been 4 in RAID 5 or something. No, it wouldn't be RAID 5. That it works out to these numbers. It could also be that back then they actually used 160. So that's why I think it was 2 drives in RAID 10. So, okay. Okay, so for any given query, there's more than one possible execution plan. If we just pick a simple query, select from table where column equals. I could use an index or I could do a table scan. When does it do one and when does it do the other? If I use the index and then I have to go back to the table, that's assumed to be a random I/O. Eventually it's going to be quicker to just scan the table. Because when we scan the table, we can do the optimizer says we can do 1,350 IOs per second versus 320 doing it random. So let's see. If you look at the formula, one key lookup costs approximately 4 pages in a scan. It's 4.2 if you work out the formula, but that's only the I/O portion. Earlier I said there was also a CPU portion, and there's some complications in how you add the pieces together. By the time you do that in a non-parallel plan, the crossover from an index seek with key lookup to a table scan seems to occur at around where it's 3.5 pages per key lookup row. If my query brings back, if my selectivity is 1,000 rows, then I know when the crossover occur in a table of about 3,500 pages. So the formula is not a percentage of the rows. but the ratio of rows to pages. So apparently no one guessed that when they were just guessing. This is why it's always better to just reverse engineer the formulas. I don't know how many people like doing that. No? Okay, well, doesn't matter. Now, in a parallel plan, which I'll get into the way the formula works a little bit, at higher degrees of parallelism, the crossover occurs closer to 4 pages per key lookup row, which means the CPU part of it is less important. I'm thinking I missed a slide, but okay, it doesn't matter. We'll get to it later. Every now and then I come across people who say hash and merge joins are bad. Does anyone think that? No one wants, I guess this is an obvious setup, so no one wants. Anyways, you write your query, it does a join. You know there's indexes on it, you're expecting it to use an index. But sometimes it doesn't do an index, it doesn't use the index in a seek, or it does a scan, and then there is a hash or merge join. For some reason, people associate the bad things happening with the hash and merge join. They don't associate it with the fact that you are no longer using the seek, but are using doing a table scan. So hash and merge joins are actually very efficient ways of joining very many rows. Now I happen to pick a query where, these are more or less the same number of rows. In this case, the loop join is the most efficient according to the plan. It happens the indexes work out that I can just do a merge join. It's moderately more expensive than the loop join. The hash join is much more expensive. Well, was that about between about 3.5 times? I do want to say, if I do a loop join, this operation, I get the rows here. For each row from here that meets my search criteria, I get all rows from this table. And that's essentially treated as a random I/O for costing purposes, even though we may be getting the rows in order. They're still not, they're not contiguous, but instead of the arm just bouncing back and forth, it could be sweeping across the disk, but the optimizer doesn't seem to take that into consideration. If we look at the join portions of the plan cost, you can see that the loop join has a very small CPU cost. The hash join has a very large CPU cost, 0.0177. The merge join is about 1/3, approximately 1/3 of the hash. And if you notice, the estimated number of rows is 2.3. It's 1 for the loop join, 2.3 for the hash and merge. I couldn't get it to match up exactly. That's funny. I don't have a sort in here. Okay, I think I understand. If I had a sort operation, the I/O cost, it has low CPU cost and it has an I/O cost of this. If you add this with the merge join CPU cost, you get a number very close to this. So, so basically, if instead of doing a hash join, I sorted it and then did a merge join, according to the plan, they're very similar in cost. Okay, so now we can, if we were to try to build a formula for the loop, hash, and merge joins. The loop has no fixed cost. It's only a cost per row, and it's relatively low on the loop, on the nested loops part. But the index seek, each time I go and get a row, it's treated as a random I/O, so I pay this fairly substantial I/O cost. In the hash join, I pay a very large fixed cost, but for multiple rows, I'm just getting additional rows. I do the index seek once, and I just go get subsequent rows. In the merge, I have a lower CPU cost and a fairly low cost per incremental row on the CPU side. So basically for very few rows, you're probably not going to get and you have indexes available, you're not going to get a hash or merge. It's going to be a loop join. But for larger row counts, the lower incremental cost of a hash and merge might outweigh this cost that you're paying on the loop join. And where shifts from using an index to doing a table scan is very similar to the key lookup. So basically, yes, for just use a single table seek with key lookup and the loop join is very similar. Okay, where am I? For those of you who don't like numbers, let's just take a look at it qualitatively. Loop join, I have 0 fixed cost, but I have a fairly high incremental cost. The hash, I have a high fixed and a medium incremental. On the merge join, I have a medium fixed cost and a low incremental. You might ask if the merge join components are always lower than the hash, why would I ever use a hash? Well, the merge has additional requirements that both sources are in sorted order. So if I don't meet that condition, I can't do a merge join. So I can either do a hash join or I could sort my results before doing a merge join. And I just mentioned that if I did that, my cost structure is similar to a hash join. Yes?
Have you seen any cases where the merge join will differ depending on whether one of the inputs would be unique or not?
Oh, yes. I'm sorry. Okay, this is a regular merge join where it's the join condition must be unique from one of the sources. If it's a many-to-many join, you can't do a regular merge join. You do what's known as a many-to-many merge join, and that has a different cost structure. And back in SQL Server 2000 days, I've seen that behave very badly, but I couldn't seem to replicate it. So if you see a many-to-many merge join, just be alert. And there's some interesting behaviors. You would think the merge join is very efficient because you take two sources, they're in the same sorted order, you find your starting point in each, and you just work your way down. It's basically like doing two index seeks. You would think that would parallelize, work in a parallel execution plan very well. Apparently it doesn't. Bad things can happen if you have a parallel merge join, but that's a pretty complicated subject. I don't know if we want to get into that. Okay, so to prove what I said about the key lookup ratio, let me now pick a bigger table. This table has 5.6 megabytes, which works out to, I believe I want this number here. So basically, at the leaf level for the clustered index, there's 699 pages. Let me write my query where I try to pick these numbers so that it works out close to 699 divided by 3.5. And you can see I got them pretty close. What's interesting is, notice my range here. Is that 106? Oh, I'm sorry, actually, let's look here. 106 to 141, then 106 to 142. So this one is a scan, and it's actually saying it's slightly lower in cost than this. So why didn't it just basically do a table scan here? Because presumably, a table scan with these search arguments should be just slightly lower in cost than this. So when the execution plan crosses over, it's not exact. It's very close, but not quite. So I don't know of a good explanation for that. Now let's take a look. This is the key lookup, the first query, which uses the index and the key lookup. You can see it's 198 executions, meaning from the index it found 198, it thinks there's 198 rows, so it knows it has to do the key lookup 198 times. Now, okay, but you notice the I/O cost is still this, and the CPU cost is still this number, which is true for a single row. That's the cost, the I/O and CPU for a single execute. In fact, we have 198 executes. So we take this 198, multiply it by the CPU portion of the cost. But we don't multiply it by this. We have to multiply only a fraction of the 198, probably like 90%. And there's actually a formula that you can map this to. And we end up with a subtree cost here. Here's the table scan. And this more or less, if you take the, let's see, 0.52, I'm sorry, so there's 699 pages, divide that by 1350, and you get very close to that number. So, oh yeah, so when you're looking at an execution plan and it's a scan, if you see 1, you know the table you're scanning is about 10 megabytes. If you see 100, you know the table is a gigabyte. So from looking at the plan, you know on a scan, you know pretty much how big the table is. And if you're doing an index scan, you know how big the index is. So yeah, this gives you more or less the crossover. Okay, so this is a simple representation. If I use an index and then did key lookup, I have very low startup cost. Oops, sorry. But if I increase the number of rows, the cost of my index with key lookup plan increases. I'm paying that I/O cost for the rows, which is fairly substantial. A table scan, I have to scan every page in the table. It's a high fixed cost. But you might think there's no incremental cost in a table scan, but in fact there is. So basically every row that meets your search argument, there's a slight cost assessed to it. So I can't really do it in PowerPoint, but there's a very slight, ever slight slope in this line here. Okay, so if our model was accurate, right around here, there shouldn't be much of a difference which execution plan I pick. But that's assuming the model and reality are the same. What if it isn't? This is my theory. What if my actual was this? What if my actual was this? If I change execution plans right here, so basically I was on this cost structure up to this row count. At this point I switched to a table scan. In fact, I was following this cost structure, and when I switch, all of a sudden my table scan is much less. If in fact this was my cost structure, I get up to this point here, then I switch to a table scan. So my cost increases. And this is why when you look at an execution plan, it's a table scan. The optimizer thinks the table scan is more efficient than the index seek with key lookup. You force the index and it runs better because there's a discrepancy, a significant discrepancy between the model and what's really true in your situation. Okay, remember I said the plan assumes a model of 320 random IOPS per second, 1350 on sequential operations with this ratio of sequential to random pages per second. And that this was, it loosely made sense based on a hard drive that was available before SQL Server 7 came out. What's happened in the 12, 13 years since then? The very latest hard drives I can buy are rated for like 200 megabytes per second. I'm sorry. Even like a few years ago, the hard drives we buy can do 100 megabytes per second. The very newest can do, I believe, like 190 megabytes per second. But I only put up 100 here. If I'm doing 100 megabytes per second, how many pages per second am I reading? It should be this number, but I've been known to make goofs before. There's 128 pages in a megabyte, right? Yeah, okay, then I did this right. So if I'm doing sequential, I'm reading 12,800 pages per second off of a single hard drive. The hard drive today can do about 200 IOPS per second. Now it depends, if you buy a 3.5-inch drive, it's different from a 2.5-inch drive because it's a smaller platter. The seek times are a little bit less. So let's not quibble over that. What's the ratio of these two numbers? It's 64, assuming I did my, I think I actually gave this in Munich last month, and I had an extra 0 in there. So I had to correct the slide and alert them. So, you know, like jet lag, whatever, I may have been drinking when I did the slides. Just, the theory is right, just check the numbers for me, all right? Okay, so 64 and 4, that's a huge difference. But a lot of databases are on a SAN. Whatever you hear about hard drives doing 100 megabytes per second, in a SAN, you're not going to get that unless you follow the, the Data Warehouse Fast Track Reference Architecture. In there, they take 2 disks and make a RAID group out of it, whereas, you know, like most people, when they do their SAN, they take what's common is like 4 plus 4, 7 plus 1, 14 plus 2. There's certain combinations that are popular. When you do those combinations, you may end up with 10 megabytes per second per disk. But the IOPS, in a SAN, there's a little bit of overhead because you have to go through more layers. So the hard disk in a bare hard drive could do about 200 IOPS. In a SAN, it might do 190, but let's just not worry about that difference now. Take this ratio, you get 6.4. That's very close to this ratio here. We don't need to quibble over 30, 50% difference. All right. Okay, so should we complain to Microsoft that we need to reflect current hard drives if we're in direct attached storage? Because this ratio is off by more than a factor of 10. Assuming you're a complete disk system when you're configured, the ratio sequential to random is 64. And if you follow fast track, you will be in this range. You can also do it with direct attached storage. If you follow that and your data is on disk, you can do sequential blistering fast, but the random IOs are not much faster than they were 10 years ago. So your execution plans are just completely off. So should we complain to Microsoft to change the ratio? Before we do that blindly, let's keep in mind, a lot of people are already on solid state disks, and more people are probably going to it. What's the IOPS character?
Yeah, could you just clarify the feature about SAN and sequential IO, the 10 megabytes per second? It's a bit low.
I don't completely understand it myself, but this is my best understanding. In the SAN vendor's view of the world, they have this hugely expensive storage system, and it's serving multiple hosts. And hosts is like your database server, a file server, whatever. So basically, the disks in your SAN are shared between multiple hosts. And they don't want any one host to grab all of the I/O. So they put in limiters to prevent you from flooding the disk queues. because if you take a look at this 10 megabytes per second, that works out to, if you're doing 64K IOs, what does that work out to? 150 IOPS? So I think the reason in a SAN you get about 10 megabytes per disk doing sequential is that even though you're doing sequential IO according to the disk layout, it's basically issuing one IO at a time at 64K. And it can do 150 IOPS at 64K. That's what I think is going on. I know that in Oracle they can force like 256K IO in a scan. That's an IO that gets sent to the disk. You might be able to do it in SQL, but I never seen a live SAN configuration that did it. And I had a reliable source told me 27 megabytes per disk was achievable in that. So it might not be 10, but it might be 20. But typically, when I go to a customer, I look at their SAN, I measure the IO throughput. I'm seeing 10 megabytes per second per disk while doing a table scan. I don't think you need to worry about it when you're doing transactions, but do not follow the normal SAN vendor disk layout in a data warehouse. Either follow fast track or use direct attached storage. Okay, okay, but a lot of people are, if you run into disk bottlenecks, okay, this solid state storage is now pretty cheap. Let me give it a try. What are the IO characteristics of an SSD? There are a lot of different SSDs, and they have like a range of IO parameters. I'm just making up some numbers here, but it's not far off. There are SSDs I can buy that can give me 20,000 IOPS. SSD vendors like to quote IOPS in 4K, but we need IOPS in 8 kilobytes. So you need to adjust their numbers a little bit. If you do sequential IO on an SSD, it may or may not be any faster. It might be a little faster because you're doing big block IO. So you get more 8 kilobyte pages. So this number might be reasonable, but I'm going to ignore the difference and just say the ratio is essentially 1-to-1. So it's off from the plant optimizer cost model in the opposite direction of a data warehouse disk layout. So basically your optimizer cannot make a good assessment if it doesn't know what type of disk configuration you have. Do you have a standard SAN where they're inhibiting sequential? Do you have a direct attach or a fast track reference architecture? Are you SSD? Now, the other thing was the optimizer assumed that it's going to do disk IO, so the cost model reflects what it thinks IO costs are. For those of us doing other transactional database, what buffer cache hit ratio is common nowadays? 99.5, 99.78, 99.9, maybe even 100. So all our data is in memory. What is the cost of doing a key lookup in memory versus doing a table scan in memory? Turns out one key lookup row is about the cost of one page of a table scan. So if your data is in memory, it kind of behaves like the SSD. So depending on whether your data is in memory, on hard drive, whatever, you can get wildly different numbers. So remember when I showed you this? The actual and the theory could be off by an order of magnitude. So this is why you can get wild discrepancies. It's not something that's easily, there's no magic thing that they can do to SQL Server to fix it. You have to be aware of it and know how to make adjustments. Yeah, sorry, I don't have a magic button. I built from the AdventureWorks database, I put in some parameters and bring up the execution plan. So here's a loop join for, I don't know, I believe it was a couple hundred rows. So you can see this part has all of it because it has to do something like 200 key lookups to it. So, sorry, 90% of 200 times the random I/O cost is a pretty big number relative to this. So all the cost is here. Let's see, I did not force this query plan. So it did an index seek, it sorted the data, and then did a merge join. So it's saying these two are about the same. If you recall, this was for 106 to 92, this is for 106 to 93. And then over here, I forced it to a hash join. So it's just a hash join, and it's saying this one is a little bit more expensive. Even though I said these two combined is about that. Well, not entirely, it's close, it's not far apart. So here you have a case of a loop join shifting to a merge join or hash join, depending, with a table scan. Let's see. Now this rate crossover is not quite at 3.5 to 1, even though this part is. Notice that the merge or the hash is a significant component. So that pushes out the crossover when a join would shift from a loop join to a hash or merge with a scan. Now you can tell people why an index is used or not used. And notice I left out covered indexes. A covered index, there is no key lookup. It's pretty much always going to be used. I want to skip this is just the cost details of the loop join. You're really better off taking the query, plugging it into Management Studio, run it against the AdventureWorks, and see the numbers yourself. Let's see. So here are the join details. Insert updates and deletes, they're really complicated. Connor has some very detailed explanation. As a matter of fact, there was a session at PASS on inserts, updates, and deletes, which in the code, it's all update. So in the code, when they say update, they mean any one of these three. But just quickly, I think Gert Draper's put out this number. I don't know if he took it from someone else. He just said that if you're modifying a large number of rows and he just picked 25%, you might consider dropping the index if you have that freedom, doing the insert, then putting the index back, as opposed to trying to insert or update with the indexes in place, the non-clustered indexes in place. In deletes, if there's a foreign, if you're trying to delete a table, how does this work? If you're deleting from the table and another table foreign keys back to it, if you delete your row, you have to make sure the rows are gone from that table. If there's not an index on the foreign key in that table, you're doing a table scan. So this is if you delete from, if you're doing deletes, check the execution plan, see if there's a table scan on a foreign key relationship. I think a lot of people don't delete from their tables, they just leave it in there. So I don't know if it'll affect you. Is this too heavy? Or is it in a manner that you can use? So all the complicated details, I think you can set it aside. Just remember the random to sequential ratio affecting when an index is going to be used, or you'll use a loop join without going to a loop join with the index versus a table scan. Pretty much that lets you answer questions on why the index, but to support it, there was a lot of calculations. And the other versions had even more calculations because I worked out in detail how the formulas were worked out. So if we had a parallel I'm sorry, how much time do we have?
more.
Okay, good.
Questions.
Okay. Let's take a look at parallel execution plans. If you have a parallel execution plan, you see the yellow dot with the 2 arrows in it. Now, not all the steps might have a parallel thing. So let's see, scan with a dot, hash join with a dot, but you also have distribute parallelism. So if my source has relatively few rows, it doesn't try to do a parallel scan of a small table. It just uses a single thread, scans the table, but sends it out to all the threads working on this query. If I work on a lot of rows from one operation and I have to send it to another operation, that's called a repartition stream. So you might think about that in a parallel plan. If you have to pull 1 million rows, work on it with multiple threads, and then each thread has to send it to the next step, which might be done on a different thread. That's not a cheap operation. And then finally, if we worked on it with multiple threads, the output has to go, apparently when you get your results, that comes from a single thread. So if you did things in parallel, at some point you have to gather up all the threads back into one. So you see a couple of extra operations. Now there's also this thing, bitmap. Basically, it's a more efficient way of doing a hash join. There's no reason you couldn't have done it in a non-parallel plan, but the theory was that it improved large hash joins. So if it improves large hash joins, it's also a parallel join. So it's only enabled in parallel execution plans. From my measurements, this could significantly improve the efficiency of your hash join. A lot of people gave out the recommendation on a transactional database to disable parallelism, set max degree of parallelism to 1. But the thing is, you don't necessarily have a pure transactional database. It could be like medium-sized reports or small reports. These things, it might have a hash join, and it might run a lot more efficiently if it could be a parallel plan. You might, considering our servers have so many cores, if you were enforcing the policy, max degree of parallelism 1, you might consider lifting that to 2, just so you can get this bitmap in a hash join. Let's see. So anyways, these are the 4 operations peculiar to parallel execution plans. Distribute streams, repartition streams, gather, and then the bitmap, which is just so happens to occur in parallel plans, even though the theory is it doesn't have to. Let's take a look at a specific query where I forced the degree of parallelism. So I forced it to non-parallel here, 2, 4, 8. You notice the degree of parallelism 2 is slightly less expensive. And then going to 4, it's just a little bit lower. You can't tell from just the percentage numbers, but if you were to look at the detail, you would find going to 8 is even lower. So let's take a look at what's happening. Degree of parallelism 1, my I/O is 810, CPU's 65. Degree of parallelism 2, I/O remains 810, but CPU has gone down by a factor of 2. This continues with degree of parallelism 4 and 8. Now this was done on a system with 16 cores. If I were to push this to, actually no, I'm sorry, I think this might have been done on a system with 32. If I did it on a system with 32 cores, I pushed it to 16, I would get another reduction by 2. But when I go to the last, when I go from 16 to 32, there's no change. So I think basically what they're saying is, well, your scaling isn't linear, but rather than factor in the slight nonlinear, I'll just take it out at the end. So the last doubling of processors, you don't get a reduction in the CPU. Now I did doublings here, but if you put in like 6, I believe you would get a CPU cost reduction by a factor of 6. So CPU is reduced by the degree of by the factor of the degree of parallelism. The I/O cost is fixed. So the assumption is that you have a saturated disk system. If whatever I/O I get from it with one thread, if I throw more threads at it, I don't get any more I/O out of my disk system. If I had a weak disk system, that's true. Matter of fact, a single thread today could probably saturate, like 30, 40 disks doing random. Actually, only 2 or 3 disks doing sequential. If I had an infinitely powerful disk, which unfortunately is also very expensive, the more threads I throw at it, the more I/O I get out of it. So in random I/O, it's very hard to get that. Random I/O to hard disk is very hard to get that. But if I followed something like fast track for sequential operations, I can you remember the purpose of fast track was to match the memory consumption rate of the processor cores. Now, on the system that they did, they said for our reference query and reference processor, we could do 200 megabytes per second per core. So if I had a 16-core system, I'm going to configure 3.2 gigabytes per second in the disk I/O system. So basically, in that system, the more threads I throw at it in a sequential operation, I'm going to get proportionately more I/O out of it, almost. So that differs than what the optimizer assumes. So you could get into a situation, I haven't really found a hard case where it does not, because the optimizer picks the plan with lower cost, just the fact that I reduce CPU by a hair, I will usually almost always get a parallel execution plan. I never inhibit a parallel plan. The issue is, if I were to look at my parallel plans, it might seem I'm only getting marginal gains out of the non-parallel plan. But in reality, I could get nearly linear scaling, or I might not get good scaling at all. But in general, it's very different. So if you're looking at an execution plan, don't worry about the fact that it says parallelism does not contribute much. If you set up your disk systems right, you could get a lot out of it. Oh yeah, if you have solid state disks, then if you use an array of solid state disks, then you can get pretty much however many threads you throw at it, you will get that random I/O. So this is like one area you need to disregard what the optimizer is telling. You need to be careful on the interpretation. Yeah, okay, this pretty much just summarizes what I said. This is not really related, but what happens if I have a lot of indexes? For every index I have, I greatly increase the number of possible execution plans, which would increase the compile cost. It doesn't factor into the execution plan, but only factors into getting it. If I have a lot of indexes, every time I do updates, I have to maintain those indexes. These are related. They're just there. It's not related to the title topic. That's all I had for this slide deck. I was told people were interested in parallelism. But that's a very complicated subject that isn't really going to be covered in 20 minutes. And it can't be done that easily. Do people want to see it, or just want to take questions?
I think maybe you have something from your other presentation that maybe summarize.
On parallelism. Let me see if I can find. well, this, let's start with this one. So this is selected queries from the TPCH benchmark. So I didn't run it in a manner that meets the publication requirements. I ran it in a manner that suits investigating what's going on. So what I'm plotting here is, I'm trying to bring up the, I need to go to, where is the presentation mode?
Slideshow at the top.
Shift F5.
F5? Shift F5. I just switched to this PC, which is Windows 7 with Office 2007. I'm still used to 2003, sorry. This is the Vista experience. Slow to... at these events in the US, sometimes the Microsoft rep will give out like free software packages. I keep asking, do you have any more Windows XP? But I'm pretty happy with the Windows 7, so I don't need the XP anymore. You couldn't buy it anymore, right? Okay, top chart is selected queries, CPU normalized to the non-parallel query. So I just ran the same query at varying degrees of parallelism. Notice, so where's my mouse? So this is CPU. If I go from degree of parallelism 1 to 2, my CPU consumed went down by 50%. The theory...
are you talking about sort of real CPU used, or are you talking about in the execution plan? What is?
No, this is real CPU used. So the theory is, if I run with 2 threads, each thread does half the work. The total CPU consumed should be about the same with a slight bit of overhead. Have a question up there?
It's the max stop setting.
I did this with max stop,
Yeah.
right? And then, but if I continue to increase parallelism, where's my mouse? Sorry. From 2 to 4 to 8, the CPU is more or less flat, which is kind of what I expected. This is the effect of the bitmap operator and the hash. For this particular query, it cut my CPU for it in half. So that's CPU, but if we go, I keep losing my mouse for some reason. Oh, sorry. So in this is speed up. So that's the duration it took to run at degree of parallelism 1 divided by the duration at the higher parallelism. So going from 1 to 2 CPU, sorry, where is my mouse? Where does the mouse go? Okay.
It's like this for you when you don't use it.
All right.
It's really annoying.
It's a PowerPoint feature.
Okay. Where's a, okay. So the speed up, I go from degree of parallelism 1 to 2. The theory is I double the speed at which it runs, but I'm getting close to 4x. So this is why I say, even if it's a transactional server, you might consider setting it to 2.
That is because the bitmap.
The bitmap and the hash. Most of these places where you get super scaling, where the CPU goes down when you go from parallelism 1 to 2, is because of the bitmap and the hash join. But if I continue to push, now this was done on an 8-way Opteron system at the original hypertransport speed before they bumped it up from 800 megahertz to 3.2 gigahertz. Basically, AMD sat on the 800 speed for a long time to help the system vendors from not having to refresh the plat. It's for upgradability. But finally, they said, well, it's too old. We have to now up it. So I ran it on an older system. So if I keep pushing the degree of parallelism, all of a sudden my CPU goes up. And what that is I'm content. There's contention for some resources. If I had run the extended events or await stats, I could have probably pinpointed it. But I hadn't built up that collection mechanism yet. So pretty much most of these, there's a big drop in CPU. There's more than a 2x speed up going from degree of parallelism 1 to 2. But at the very high degrees, all of a sudden, I don't get any more speed up. And as a matter of fact, it may even run, not only does it burn more CPU, but it may actually run slower as I try to push the degree of parallelism to the very high points. So this is why on a big system, you need to, I suggest you do your runs at different degrees of parallelism to look to see if there's a good point. I think if you have a mixed workload business system, you might pick 2 or 4 for default and specifically identify queries that either should not run without parallelism or run at higher degrees and just use the option max stop there. You might be able to use the resource groups, but I haven't found anyone willing to use that. So it's a good idea that people requested, but they request a feature, but then they decide, I'm not ready to use it yet. So you made Microsoft do a lot of work, and then, well, I mean, it happens. They've been lied to before, so they'll get over it. Okay, let's see. Oh, I just changed the scale on this. Most probable cause is the bitmaps. Bitmap filters are great. So I bugged them because they're so great. Sure, you want to reserve them for the bigger hash joins, but I want it turned on for degree of parallelism 1. For that rare situation where I disabled parallelism in my transaction processing system. I don't know if they'll do it, but they've put in other things I've asked for before. Even though the official responses go bug off, they put it in later. I don't quite understand it. Let's see, small queries. The way the parallel execution plan works is there's a cost threshold of parallelism. The default value is 5. So if the plan cost is 5 or greater, it will consider a parallel plan. If the parallel plan has a lower cost, it will use a parallel plan and it will generate it with the max degree of parallelism allowed. And then at runtime, it makes a decision on the actual degree of parallelism. But the thing is, you could find that this small query could actually kick off a full parallel plan. And this actually happened with an ISV that did the restaurant point of sales. I don't want to mention names, but they eventually sold to Starbucks, where the volume was very important. Not that you need, okay. So one of their transactions had it wasn't indexed well, and it had a plan cost of like 10 or 20. And so they were supporting a medium-sized customer at the time, and they had a 2-socket dual-core system, and it ran kind of sluggish. So instead of hiring an expensive consultant, they went out and bought 2 big 4-way systems, which 4 processor sockets, 4 cores each, 16 cores, did not run any better. It was dominated by this one query that was just barely eligible for a parallel plan. So even though I quadrupled my compute power, I also quadrupled my degree of parallelism on that one query. And apparently the overhead for setting up those queries pretty much is not accounted for in the plan, and basically ate up all so the overhead for setting up a degree of parallelism that high was about equal to the extra number of processors they got. So they were just stunned. They just spent like $90,000 on 2 big boxes because they were clustered. And the reason I bring this up in a critical manner is because when they called solid quality, they complained about our rates. So the cost to them for us fixing this for them was much lower than the cost of their machines. So I went and told our business manager, no more discounts for these guys. That's why you want to hire an expensive consultant before you buy expensive hardware. The reason you hire an expensive consultant is if the consultant was cheap, would you listen to his advice? So you tell your boss that you need to hire this really expensive consultant. I might say exactly the same thing you said, but your boss doesn't listen to you. He will listen because he just paid a huge amount of money for this advice. There are these funny things, they're true. Read Dilbert and you can, but they don't get into all aspects of it. So small queries, be wary of it that the plan may kick off a max degree of parallelism when it does no good. So is there a good example of that? No, I don't want it in here. I want it a little further. Queries that go negative. So the top is query time. So if I increase my degree of parallelism, I reduce the amount of time, it speeds up. But if I push it beyond a certain point, it actually runs slower. So you need to watch for that. Now, some of these are small queries, but some of them are not. Yeah, you see they ran in, so this is time in seconds. So you can see these are queries running in about a third of a second. I would be very watchful for parallel execution plans that go into queries that run less than a tenth of a second. So that might be the other criteria you want to think about. Do you want to kick off a parallel plan for queries that run very quickly? Because if it's a user waiting for it, is he going to notice a difference? If he is, yes, maybe you want, and he's important. If it's someone that you want to suffer because they were rejected your whatever, go ahead and you control the database, you're God. I think that's pretty much all I wanted to cover. It's pretty complicated, but there's one that's a good thing and the other is a trap that you want to look for. Okay. Well, thanks for attending. I hope this wasn't too heavy.
Thank you very much, Joe.